Hello Precalc folks, welcome back for some more trigonometry. Today we're going to go on with lesson 5.2, which is about solving trigonometric equations. Now in our last lesson we already looked at solving some simple trigonometric equations. Here we're going to get into some more complicated, we'll just say it, uglier trigonometric equations. Alright, we're going to break this lesson down into 3 parts. Here's part 1 for you. And in problem 1, what we're going to do is we're going to kind of show you 2 problems at once. There's going to be 2 different ways we ask you to express solutions for trig equations. Okay, one's going to be the idea of giving all solutions on the interval from 0 to 2 pi. In other words, within one lap around the coordinate system. And the other thing we're going to ask for in part B is just flat out find all solutions. Now, like we saw last section, one of the tricks with solving trig equations is there's multiple solutions to a trig equation. There's actually infinite solutions. Okay, so that's going to be the 2 different things we do. We're going to look at giving all solutions within one lap around the coordinate system. There might be 1, there might be 2, there could be more than that. And then in part B, we'll look at finding ways of expressing the infinite number of solutions. Now we'll start off with part A because I'm going to say that's the more straightforward question to answer. So we want to solve 3 sine x minus root 3 is equal to sine x. Okay, we want to figure out what x makes this equation true here. Okay, now this looks kind of ugly, but really my approach to this is going to be to turn it from an ugly trig equation into something simpler like we looked at last section. So for that, what I'm going to do is I'm going to get everything with an x on it on the same side of the equation, just like if there weren't any signs in here. So I'm going to subtract sine x from both sides of this guy. That's going to leave me with a 0 on the right, and then 3 sine x minus sine x will just be a 2 sine x on the left, and then still minus the root 3. So we got all our x's on one side of the equation. I now want to get all my other stuff on the other side. So for that, I'm going to add root 3 to both sides. So that'll leave me with a 2 sine x equals root 3. And then finally get the sine x by itself. I'm going to divide both sides of the equation by 2. Which will leave me with a sine x is equal to root 3 over 2. Okay, now I'm going to say I'm back to the simple type of equation that I was doing in the last section. Okay, so first step with these is going to be to isolate the sine of x or the cosine of x or the tangent x, just like you would isolate an x in an equation. Okay, from here I want to solve, so I'm going to go to my coordinate system. And I need to figure out which quadrants are going to have solutions. In other words, which quadrants are going to be positive sign values. Alright, well I know the first quadrant's always positive, so I'm going to have a solution in the first quadrant. And then since sine is opposite over hypotenuse, okay, I know I need a positive opposite side. Therefore, I'm also going to have a solution to this second quadrant, where again, when I make my reference triangles here, we've got positive opposite, positive hypotenuse, and then this triangle here would also have a positive opposite and positive hypotenuse as well. Okay, no, I don't have any solutions in the second or the third or fourth quadrant because here I'd have the negative opposite side with a positive hypotenuse. That'll give me a negative sign. Okay, like we said, sine is opposite over hypotenuse. So for these reference triangles, I know my opposite side has to be a root 3. Hypotenuse has to be a 2. Okay, root 3, 2, 1. Looks like we're looking at our 60, 30, 90 right triangle. And same thing on this side, opposite root 3, 2, 1. So we have a 60 here for a reference angle as well. Okay, so as far as my actual answers go then, I've got a solution of 60. and then also have a solution of 60 short of 180, in other words 120 degrees here. Okay, and that's all the solutions between 0 and 2 pi. In other words, all the solutions within one wrap around the coordinate system. Now I want my solutions between 0 and 2 pi. In other words, I want them in terms of radians. So I'm just going to take each of these and multiply them by pi over 180. Okay, or if I know that 60 is just pi over 3, I know I have x equals pi over 3. And then 120 is 2 pi over 3, so we just say 2 pi over 3. Okay, so that's all my solutions between 0 and 2 pi. Okay, kind of the more straightforward type of question to answer. All right, so for part B, the difference is instead of finding all solutions on the interval 0 to 2 pi, we're going to express all the infinite possible solutions to this equation. Okay, same equation, which turned into sine of x equals root 3 over 2. Okay, same solutions to kind of start off with. I'm just going to sketch out that graph here quick. We had a solution of pi over 3, and then another solution of 2 pi over 3. That's what we just did in part A minute ago. Now here's what I'm looking to do with this. Okay, I have two solutions within one wrap around the coordinate system. I'm going to make my picture a mess here. But if I think in terms of coterminal angles, if I take this solution of pi over 3 and I add a full rotation to it, I get back to an angle that's coterminal with that pi over 3. So a different way to write it, same angle though, which would also be a solution. Okay, I could also add a second rotation or a third rotation, and I'd keep coming up with solutions. Every time I add a rotation, I get another solution. Same thing with a solution of 2 pi over 3. So the way we're going to express that idea is we're going to say that x is equal to pi over 3 plus, I'm going to say 2k pi, where k is an integer, meaning that every time I add a multiple of 2 pi to this, so 1 2 pi or 2 2 pi's or 3 2 pi's, I'm going to keep spinning around and getting to the same spot here. Okay, I can do the same thing with the 2 pi over 3 plus 2k pi, because every time I add a rotation either forward or backwards to that solution, we'll come up with another solution that works. Okay, we'll put a little disclaimer on this to begin with. K is an integer, or we'd say that k is an element of k. That's how we write the integers. You don't need to write that every time. We'll just say it the first time around. We all understand that k is a counting number, an integer. All right, so that's the basic idea we're working with, turning ugly looking trig problems into simpler trig equations, and then expressing the solutions, whether we're talking between 0 and 2 pi or the infinite solutions. Okay, obviously the infinite solutions part will be one of the tricks for this section, but we'll get it figured out. What we're going to do the rest of the way is look at some specific types of trig equations to solve. We're going to do one more in this part of the video, then let you practice a little bit. Okay, so kind of different specific situations all building off that idea we just did. Okay, problem 2 I'm going to say is the extracting roots example. Okay, find all solutions. And as you look at this equation, the big difference is this squared here. All right, we're going to need to get rid of that. We're going to need to extract it. That's why this one's called extracting roots. We'll start this problem off the same way we did the last one. We want to get that tangent by itself. So I'm going to add 1 to both sides of the equation. That'll give me a 3 tangent squared x is equal to 1. I'm going to divide both sides of the equation by 3. That'll leave me with just a tangent squared x is equal to 1/3. And once we have the tangent squared by itself, I can deal with the squared. I'm going to square root both sides of this equation. And what that's going to leave me with is the square root of tangent squared is just a tangent. We'll say tangent x on the left, so we have it by itself, is equal to, now anytime you take a square root in an equation, you need a plus or minus, so I'm not going to forget that, plus or minus. And then we'll call this square root of 1 over root 3, just 1 on top, because the square root of 1 is 1, and square root 3 on the bottom. Okay? So really the same thing, only difference is we have the square root, which is going to give us the plus minus. Let's show you how to deal with that. So when I go to my angles and standard position, and I go to decide where the solution is going to be, since it can be either positive or negative, I know I'm going to have solutions in all 4 quadrants. Okay, because tangent's either going to be positive or negative in any of the quadrants. It can't be something besides that. So I know I'm going to have a solution in the first quadrant. I'm going to have a solution in the second quadrant, third quadrant, and fourth quadrant. And that's again because we have the plus minus here. All right, let's figure out what those solutions are. Tangent is opposite over adjacent, meaning that when I make my reference triangles here, I've got my opposite of 1, adjacent side of root 3, meaning my hypotenuse is 2, so kind of the magic number I'm looking for here would be 30 degrees. I'm talking 30, 60, 90 right triangle, where the 30 is across from the 1. Okay, I'm not going to redraw those reference triangles in all these spots. I'm just going to come up with the answer, what the answers are. So we could say that x is equal to 30 degrees. Okay, I'm also going to have 30 short of 180, in other words, 150 degrees. Okay, I'm also going to have 30 past 180, so 180 plus 30 would be 210 degrees. And then finally, the last one, as my picture becomes an MS here, we have 30 short of 360, so in other words, 330 degrees. Okay, we want to put these in terms of pi's. So what I can do is multiply by pi over 180. If I do that, and I actually know that 30 is pi over 6. Okay, 150 is pi over 6 short of pi, short of a half rotation, so I know that's a 5 pi over 6. All right, 210, that's pi over 6 past pi, so in other words, 7 pi over 6. And then 330 is pi short of 2 pi. I'm sorry, pi over 6 short of 2 pi, so that'd be an 11 pi over 6. Okay, so those are some shortcuts I can use to make these calculations. Yep, or I can multiply by pi over 180 with the calculator every time. Okay, that's all the solutions between 0 and 2 pi. But what we really want are all solutions, the infinite number of solutions. So just like I did in the last example, I'm just going to add plus 2k pi to each of these. And then I'm almost done. Okay, so those are 4 expressions to generate all the infinite number of solutions. As I change k from 0 to 1 to 2 to 3 and so on, I'll get all the possible solutions as I keep counting up or keep counting down. Now the trick with this one is there's actually a simpler way to generate these. Switch colors here. Notice that my first solution, the pi over 3, and the third solution, the pi over 6, and the 7 pi over 6, differ from each other by 180 degrees, or pi, okay, so a half rotation. So rather than having two separate solutions here, expressing as two different ones, what I can do instead is I can put those together as a single solution, because every time I add a half rotation, I'll bounce back and forth between this first and third solution. Okay, so what I can do is I can combine, like we said, the pi over 6 and the 7 pi over 6 and rewrite that as x just equals a pi over 6 plus, instead of 2k pi, just a k pi, a half rotation. Because again, every time I add a half rotation, I'm going to get one of these two solutions. Okay, I can do the same thing with the second and fourth solution. And really, anytime I have solutions in opposite quadrants, like this, okay, diagonal from each other, I'm going to be able to combine them. So same idea, I can take this 5 pi over 6 and the 11 pi over 6 and write that as a single solution as 5 pi over 6 plus k pi. I suppose I also could use the 11 pi over 6 plus k pi, same difference. But again, anytime I start with 5 pi over 6 and add a half rotation to it, I'm going to keep bouncing back and forth between these two solutions. Is my picture messy enough here? I think so. All right, so I'm going to say this is the best answer we can give. Up top here with the 4 different solutions, that's still a correct answer, but I'm going to say it's not as simple as we can make it. Anytime you can combine two solutions into a single solution, do that. Okay, it's like simplifying your answer. All right, last thing for this video, problem B, same idea. There's an extra little trick to that one. Let's see if you can catch it. It's okay if you can't. Why don't you pause the video, work through part B, and then hit play to check your work and see if you got it correct. All right, let's run through B here. Same type of problem, extracting roots because I have a trig function squared. So we're going to add 2 to both sides. That'll give me a 4 cosine squared x is equal to just a 2. I'm going to divide both sides by 4. That'll be with the cosine squared x is equal to 1/2. And finally, we'll extract the root. We'll take a square root on both sides of the equation, which will leave me with just the cosine x on the left is equal to, don't forget the plus or minus, and we can say 1 over root 2. All right, so there's our simple trig equation to solve. All right, I'm going to do that right here, so I've got some room up top. Without my face in the way. Okay, again, where do I have solutions? Since it's plus minus, there's no guess or check work. I just know there's a solution in all 4 quadrants. As long as you don't forget the plus minus part on this equation, you're not going to miss that. All right, cosine is adjacent over hypotenuse, so I know for these reference triangles, the adjacent side will be a 1, hypotenuse will be a root 2, 1, root 2, other side's going to be a 1. Okay, here's our 45, 45, 90 right triangle. So solutions I come up with are x equals 45 degrees for the first one. Okay, if we're 45 short of 180, that'd be a 135 for the second solution. Third solution is going to be 45 past 180, so 180 plus 45 would be 225 degrees. And my last solution will be 45 short of 360. 360 minus 45 is going to give me a 315. Okay, I always want to convert these to radians. I know that 45 is pi over 4. Okay, 135 is a 3 pi over 4. 225 is a 5 pi over 4. And 315 is a 7 pi over 4. And what I'm doing with that, how I do those so quickly, is I'm just counting by pi over 4s. If we think of the 7 pi over 4, for example, the 5 pi over 4, the 225, I know that a half rotation is pi, so if I am pi over 4 past that, okay, pi plus pi over 4 would give me the 5 pi over 4. Okay, we're talking all solutions, so we'll say plus 2k pi to start off with. You can kind of think of adding a full rotation as kind of your starter, your way to start generating all solutions. Then you can simplify from there. Okay, then hopefully what you did is like we did in the last problem, you combine the first and third solutions as we could say pi over 4 plus k pi. And then same thing, you combined the second and fourth solutions as we could say 3 pi over 4 plus k pi. Okay, because when I add a half rotation, I'm going to get to another solution. I don't need 4 to generate this. I could do with 2. Okay, but I'm going to say with this one, we can do a little bit better. This one simplifies a little further. Okay, if we look at the angles we have, our reference angles are 45 degrees, meaning that there's 90 between the two solutions here. And if this is a 45 as well, there's another 90, and another 90. So what I can actually do with this one is combine all 4 solutions into a single expression. We could just take the smallest one, say pi over 4, and then plus, instead of adding a full rotation, 2 pi. Instead of adding a half rotation, which would just be a pi, what we'll do is we'll add a quarter rotation, which is a pi over 2. So we'll say k pi over 2. And what that's going to do is every time I add that quarter rotation, I'll get to the next solution. Okay, so this one's a little trickier, simplifies a little further than the last one. If you didn't catch that on your own, that's okay. And basically, when this is going to happen is anytime my solutions are 45 degrees and I have them in all 4 quadrants. Okay, so like we saw in the last problem, part A, we did have all 4 quadrants, but we could only do it with 2. The reason I can do it with a single solution here is there's an equal angle between all these angles. Again, that's only going to happen when everything's 45 degrees. All right, so there's part 1 of our solving trig equations lesson. Might seem a little tricky right now, especially with that infinite solutions deal. We're going to be coming back to it in part 2 and in part 3, so you'll get it. Trust me, you'll get it. Okay, don't move on to the other videos yet, though. Give the homework a shot. Make sure you're good with this part before you move on to the next part, which builds off it. Okay, we'll say for now, homework, you can do 1 through 7. They'll cover the kind of basic examples along with extracting roots. They'll give you both types of solutions you're looking for on the interval 0 to 2 pi, all solutions. Okay, give those a shot. Make sure you're okay with those before we move on. And like always, if you need help, we're here to help you out.